Hello everyone and welcome to Exploring Diana YouTube series where we explore the powerful capability of Diana one step at a time. My name is Solmos and today I will go over one of the tutorials on Diana website. The title is Bond Sleep Models in Diana. Let me describe the problem and after that I will jump to Diana environment to start simulating. In Diana, Bond sleep model described the interaction between the reinforcement and surrounding concrete. They captured the sleeping behavior of the reinforcement and the resulting traction that developed due to these relative movements. This type of modeling is important for simulating the shear interface behavior between the concrete and reinforcement, especially in reinforced concrete structure where accurate representation of the bond behavior can affect the structural responses. In this tutorial, I want to demonstrate different bond sleep models that we have in Diana. And for this purpose, I will use the plane stress rebar pull-out test example. Since in this tutorial we want to focus on the interface behavior, I want to go through the step only related to the defining and assigning the bond sleep properties. And for the other basic definition like creating the geometry, assigning the support, you can review the other tutorials or use the manual to see what we have in Diana. As you can see on the screen, we have two objects. The first one is a concrete, the second one is a reinforcement. We support the three sides of the concrete element and also apply the load at the one end of the reinforcement. Now I can move to Diana environment to start simulating and describing the bond sleep behavior of the reinforcement. This is a Diana environment. In Diana, you have a three option to create geometry: the right toolbar, the action toolbar, command console, and using the Python script and importing the model from the CAD file. Now I want to save time, so I use the Python script to create geometry and defining support and load to the model. I will copy and paste the Python script and wait for a second until Diana create the geometry. Yes, very good. I will show you what we have in this model. We have a reinforcement, we have a concrete, and also we have a support. We fix the upper edge and the bottom edge in the y direction and the one of the side edge of the concrete in the x direction. Also, we have a load. I will show you what we have. This is a prescribed deformation and we define the 1 millimeter deformation in the x direction, and also we need to define the support for the prescribed deformation. Very good. Now I want to define the material properties for the reinforcement in this model. Also, before this step, I have created a concrete material property. Is a linear elastic material properties for the concrete. Now it's turn to define the material properties for the reinforcement. Now it's time to define the material properties for the bond sleep reinforcement. I come to the bond sleep reinforcement set, click right, reinforcement properties, and in this window, for the type I want to select the truss bond sleep. I need to define the material and geometry for the reinforcement. So first of all, I come to the material. I call it rain material. And in the first part, I need to define the linear properties of the reinforcement. And in the second one, I need to define the bond sleep reinforcement. So I input the Young modulus Poisson ratio, and also the mass density for the reinforcement, 7.8 E minus 9. And I come to for the nonlinearity model. For this step, I select a no nonlinearity. I come to the bonded slip interface and define the normal stiffness modulus and shear stiffness modulus for the model. So for the bonded stiffness, we have a rule of thumb to calculating the normal stiffness. The rule of thumb is stiffness divided by the element size and multiplying a constant, usually between 80 and 100. In this model, this rule of thumb come to the value E1, E5. For the shear stiffness, and since we want to observe a more slip behavior, we use the value 100 for the shear stiffness modulus, and also no failure for the bonded stiffness failure model. The next step is defining the geometry. I create the geometry, I call it rain geometry, and reinforcement type is a truss bonded slip. For the definition of the geometry, I select the diameter and input the diameter of the reinforcement. Very good. Now I come to the update, and now we define the material for the reinforcement and also geometry for the reinforcement. Now we are one step behind the analysis, setup, and see the result. In this step, I want to define the mesh and generate mesh in this model. So I come to the mesh properties. In the geometry, I select the bonded slip and the concrete, and also for the division element size. The element size select the 30 millimeter for these elements, apply, and after that I generate the mesh. Very good. So let me show you the support in the mesh view. In each node we have a support, and also I come to the project setting. I will show you what we have. This is a quadratic mesh order with a linear interpolation for the mid-side node. And this is a two-dimensional plane strand, two-dimensional problem. After generating mesh, we need to set up the analysis section. I used the Python script for this section and run the analysis. I will show you what we have in the analysis setup. It's a structural nonlinear analysis. For the nonlinear effect, only we have a physically nonlinear. And for the executing block, we define the load step for the prescribed deformation load, and we set up a 10 load step with the factor 0.02. And for the convergence node, we select the displacement and the force convergence node. After running the analysis, I come to the result toolbar. So I select the last step in the cases. And for the output as a first selection, I select the total displacement in the X direction. And I will click right on the total displacement and show the line diagram. I come to the properties, result, diagram plot setting, and set the scale factor to 10 to have a better understanding of the displacement. The next result that I want to show you is a reinforcement Cauchy total stress. And I will show you the SXX. The maximum value is above the 400 Newton per millimeter power 2. And as you remember, we defined the shear stiffness modulus 100 in this model, and the ratio between the shear traction, maximum shear traction, and the maximum relative shear displacement is equal to the shear stiffness value, which is in our case is a 100, and it means that for every millimeter of a slip we get the 100 of the megapascal of the interface stress. Another model that I want to describe in this video regarding the bounded slip failure model is a cubic function which is proposed by Doerr. As you can see on the screen, you can see the graph and the main relationship regarding this model. Doerr proposed a polynomial relationship between the shear traction and slip, which reaches a plateau once the slip exceeds a certain value, delta U0, as you can see on this graph. So to apply this model in the diagram, I come to the geometry, come to the bounded slip reinforcement, and in the failure model, I select the cubic bounded slip function by Doerr. For the parameter C, we input the 2.06, which is approximately the tensile strength of the C30 concrete, and we assume that the shear traction level off at the slip of the 0.06 millimeter, which is about 1/3 of the total applied displacement. So I come to the update. I need to remesh the model and rerun the analysis. After rerunning the analysis, I come to the results section. First of all, I want to check the displacement. It's a line diagram. And select the last step for this purpose. It's a 0.2 millimeter, same as the previous model that we call it as a linear model. Also, in the reinforcement result, I come to the reinforcement Cauchy total stress. I select the SXX. And as you can see, we have a maximum 261 megapascal. So I come to the other result, which is related to the shear displacement and also shear traction. So the first of all, shear displacement is same as the previous model, but when I come to the shear traction, I can see the 3.91 megapascal. If you remember, in the previous model, we reach up to the 20 megapascal for the shear traction. And the maximum stress in this model is significantly lower than what we have in the linear model. And this is because the shear traction behaves differently in this model, even though the relative displacement or the shear displacement are similar in the both model. And this setup results in a much smaller area under the bounded slip curve for the polynomial model, which indicate the less total stress transfer. Now I come to the third model for the failure behavior of the bounded slip. The name of this model is a power law, which is introduced by Naokowski. As you can see on the screen, you can see the graph and the main equation regarding to this model. The bounded slip relationship, which is proposed by Naokowski, represents a stick slip behavior. It uses a power law where the traction equals a constant parameter which multiplied by the slip raised to the exponent parameter. So for this purpose, I come to the material properties. And in the bounded slip failure model, I select the power law bounded slip by Naokowski, and we need to define the constant A, power B, and where the shear slip at which curve is truncated. So we add the number 6 for the constant A, and we ensure that the initial stiffness match the linear model. And we want to define that after 0.06 millimeter, the curve will follow a softer response, which is governed by the exponent B. In this model, we consider 0.1 for the power B. After this definition, we need to update the model, regenerate mesh, and rerun the analysis. After rerunning the analysis, I come to the results section. For the displacement, check the displacement in the x direction. And for the case, I come to the last load step. Also in the reinforcement result, I come to reinforcement Cauchy total stress, SXX, is a bit higher than the previous model. And I need to check the shear displacement and shear traction. So for the shear displacement, we have a maximum similar to the all previous model. When I come to the shear traction, I can see the different value and different behavior. In this model, the shear traction distribution doesn't display a sharp peak. Along the portion of the bar where the relative displaced slip is less than 0.06 millimeter, the distribution looks similar to the linear model, the first one. Beyond that, where the slip exceeds the 0.06 millimeter, the shear traction follows the power law that we define in the material properties with the parameter A and parameter B. And the maximum shear traction reaches around the 5.1 megapascal at a slip of the 0.2 millimeter. The fourth model regarding the failure model in the bonded slip, which is called Shima bonded slip relationship. This model is proposed by Shima, and you can see the graph and the main equation regarding to this model on the screen. As shown in the diagram, this model starts with the infinite initial stiffness. To avoid numerical issue, Diana used a linear stiffness until the curve starts following the Shima relation. The traction here happened based on the two main inputs. Let me open the material properties for the reinforcement. In the failure mode, select the Shima bonded slip function. And as you can see in this window, we have a compressive strength, bar diameter, and factor to shear stress. In this model is the shear traction here depend on the two main input. The first, the compressive strength of the concrete. I input the 30, and the bar diameter here is 16 millimeter. And also we adjust the scale factor 1. Let's set as a default for the factor to adjust the shape of the curve. I come to the update, close the window, remesh, and rerun the analysis. And after that, I come to the result section. I select the last load step. In the displacement, I check the line diagram of the displacement in the x direction. In the reinforcement result, I come to the SXX and check the maximum stress in the bar, and we need to check the shear displacement and the shear traction in this model. So for the shear traction, we have a maximum 0.2 millimeter, same as the previous models. And for the shear traction, I select the reinforced interface total traction. And as you can see, we have a maximum 8.2 megapascal. We can see clearly the two zones along the bar, one with the linear stiffness and the one where the actual bonded slip function is active. The transition between these two happened around the slip of the 0.06 millimeter. Next, I want to apply the bonded slip strain model, which is developed by Shima. On the screen, you can see the graph and the main equation regarding to this model. This model is an enhanced version of the previous bonded strip relation. In this model, the shear traction not only depend on the concrete strength and the bar diameter, but also on the strain in the reinforcement bar. So let me come to the material properties for the reinforcement. In the failure mode, I select the Shima bonded strain function, and we use the setup as same as the before. So for the strength, the compressive strength 30, for the diameter 60 millimeter, and the factor for the curve is 1. I come to update, remesh, and after that we run the analysis. Okay, I come to the results same as the previous models. The first result that I want to check is the displacement in the x direction. I will show in a line diagram. And also for the cases, I come to the latest one, the load step 10. The next result is a reinforcement Cauchy total stress. And we need to check the reinforcement interface, total traction, and relative displacement. So first of all, I want to show the shear displacement, and after that, the shear traction. By checking the result, I have noticed a difference in the shear traction, especially toward the end of the bar, where the influence of the rebar strain become evident. This shows how the strain load incorporates in the interface of the behavior in this model. The last model that I want to discuss in this video is FIB model concrete. FIB model code for concrete structure 2010. This model defines a backbone curve divided into 4 segments. The graph regarding to this model is presented on the screen. From 0 to a small slip value S0, a linear stiffness is used. This helps avoid numerical issues from using a power function with an undefined stiffness at the origin. From S0 to S1, a power law is applied. Between S1 and S2, the bonded stress remains constant at its peak, which we call it tau max. Then from S2 to S3, the stress drops linearly until it reaches the residual stress, which we call it tau f. Beyond S3, the stress stays constant at this lower level. So again, I come to the material properties of the reinforcement and select the FIB 2010 bonded slip function. And we need to input data regarding this model. So the maximum shear stress 7.7, for the ultimate shear stress 3.08, for the S0 0.06, for the S1 0.08, and we need to input data for the S2 and S3. And also for the alpha, we consider the value as a 0.4. Very good. I come to update, remesh, and run the analysis. Again, I come to the results section, select the last load step, and the first result that I want to show is a displacement. Line diagram. After that, in the reinforcement result, I want to show the reinforcement Cauchy total stress in the x direction. And we need to check the shear displacement and shear traction. For the shear displacement, and the last result that I want to show you is a shear traction. As shown in the result, all sections of the backbone curve that I presented earlier can be clearly seen in the shear traction distribution around the bar. The linear part, the exponential, and the drop of the stress, and after that, the constant value for the S3. As a last remark that I want to mention in this video is we have another model in Diana for the bond sleeve interface failure mode, which is called the multilinear. Let me show you. Again, I come to the geometry, and in the failure mode, I select the multilinear bond sleeve curve. And you need to input data regarding the relative displacement and the shear traction in this Excel part, and you can see the final curve in the right side of the window. And the final result can be same as the graph that is presented on the screen now. Now we come to the end of the video. Just let me show you how you can find this tutorial on Diana website. In Diana website, you can go to the to get started and the tutorial section. In tutorial section, you can filter the tutorial based on the tutorial type, analysis type, and the modules required. So in the tutorial type, I come to the feature, and yes, you can find the bond sleeve model in Diana tutorial. Thank you for your attention. Please don't forget to subscribe the Diana YouTube channel. Thank you.